So, okay. So our next speaker is Malachi. He'll tell us about the deep learning application to Belle analysis.
Right, so I'm going to give a fairly high-level overview of some of the work that we've been doing in Belle 2 related to deep learning. And then this is just a case, an example, but we'll talk about some of the other components that involve like high-performance computing and stuff. So just as a recap for those that are unaware, so Belle 2 is an electron-positron machine detector that measures machines from the SuperCat B. The real goal here is to look for new particles or new interactions beyond the standard model. It's a fairly large collaboration. We're growing, and we're a little bit over 725 physicists, 104 institutes in 24 countries. The data volume that we anticipate or predict is about 50 times more than the Belle experiment. And our data rates will be about 40 times greater than the Belle experiment. P&L has been the lead lab for constructing the lead lab for Belle 2, and has also finished the construction of some of the detector components. This is, in fact, the largest U.S. scientific investment in Japan. And we're currently at the point where SuperCat B has been running a single beam circulation successfully in what we call phase 1. That was in 2016. We're currently in what's called the cosmic ray data taking. And then at the probably in February, we'll start wrapping into phase 3, which is a physics run. So that's the general recap. And this picture, of course, is a bunch of people and the Belle 2 detector itself. So the gist of this talk on slide 3 is kind of a workflow that we've envisioned to try to take advantage of some of the LFCs and also just the general deep learning effort that's been going on within the HEP community. So what we really want to do is we want to leverage some of the virtualization technique that we've been working at PNNL so that we can actually use the NERSC and Oak Ridge Titan to do some of our larger scale deep learning problem sets. And then the goal here is we're really working towards a full-scale demonstrator of using what's called MATEX, which I'll talk to later on in the slide deck. So the idea is that you have some physicists that have some analytical problems. Here we have Belle 2 for our case study. Then we have the layer where we have software stacks, where virtualization software such as MATEX, and also our grid software. And finally, we have access to the LCS. Those are the supercomputers within the US. So, in the context of a physics analysis, so here's a physics analysis that we've chosen, primarily because we have a good baseline for comparing the deep learning techniques versus what's currently available. So, what our analysis here is B to K-star gamma. So this is in the standard model, there's a flavor change in neutral current. Okay, and it is very sensitive to new physics, so it's a very important channel for Belle 2. It's actually one of what we would consider what's called a golden channel. So this is one of the key analyses that we'll be doing. And we are currently working on this analysis and leading this effort. And so one of the things we're looking for is essentially there's some strong constraints on the new physics in the Wilson coefficients, and I'll show you that in a second. And there's some new papers on phenomenological papers that talk about this in detail. But the bottom line is the process is you have a B, it goes through a W, radiates your photon, and you have a strange. So this is the kaon comes from that S, right? So and your B, so you have your transition here. So what we anticipate with this particular channel in the early days of physics is that we'll have some events, roughly about 50 to 70 based on our efficiencies, so that we can actually do some analysis. The goal really initially is to simply do a reobservation, because this has been observed. And then we also want to do things like the detector performance. This particular kaon here is very important in terms of keeping track of our particle identification performance, which is one of the main key investments in the US for the ITOP, and I'll talk about that very quickly. And the other measurements are like asymmetries. So moving forward, just a quick snapshot. The operator that you introduce would be essentially instead of that W, you can put whatever operator you want in your new physics. And so this this coefficient now becomes a standard model coefficient plus the new physics coefficient that is in this blob. So that's really what we're looking for. Do we see anything in that blob? That would be beyond the standard model. So the exercise we've had up to now is that we take Keras plus TensorFlow, and we're using that to do our study. And this is really, again, a pilot investigation for us to determine how well and how it compares to other techniques that are common to our community, such as TMVA. In this particular analysis, we're looking really at distinguishing that particular signal to what's called the B backgrounds, which is our dominant background. Okay, so we've limited to that. These are just the specifics of the setup. So we, of course, labeled our signals. So this is a labeled analysis. We could also do a multiple classification training, which is the next step. But currently, we only have a binomial training setup. So we split the data into our test and training, as is common. We normalize the variables. We've done a fully connected 6-layer neural net. We have a dropout rate of 15. And then we have the atom optimizer. Finally, we use the binomial cross-entropy. And then we have a validation sample within that training sample of 25% so that we can verify that everything's actually consistent and things are correct. And then for this particular analysis, we did 10 epochs. Of course, we've swept around a bit and looked at different processes. But we haven't done a fully exhausted hyperscan yet. But nonetheless, what we see in the preliminary results is that we see this is in a y-axis, the background rejection, and the x-axis, our signal efficiency. We've looked at various configurations of TMVA, so boosted decision neural nets, and then what we call tune boosted decision tree, and then finally our TensorFlow. And we can clearly see that we have a significant improvement using a deep neural net, using a fairly large data sample. Of course, this is a fairly easy, fairly simple analysis. And really what we're looking at is eventually looking at things that are much more complicated. And I'll give you a teaser of what is more complicated. And the B to K star tau tau, for example, is one of those analyses we want to look into. But we clearly see a good comparison between the two technologies. So a little closer look at the different technologies. What I want to have everybody look at really is a significance, which is in the green, versus a significance from Keras TensorFlow, which is in this blue on the right side. What you see here is this is much more of a peaking component than there, so that allows us to have more confidence in terms of our systematics and where we might want to put our cuts. The other thing to keep to note is that we see effectively a 45% gain in the significance when we use the Keras TensorFlow implementation. So that's effectively like a lot of data relative, so that's like getting a lot of bang for the buck. So the teaser that I was going to bring up is analyses that are much more complicated in Belle 2, which are the B to K star tau tau. And so on the right here, you have a schematic diagram of this decay process. So you have a B decaying to a K star, which is a kaon and a pion, and then there are taus. In this example, we have 3-pronged decays, okay, plus some neutrinos, of course. So at the very least, if you look at hadronic decay, looking at 8 tracks instead of 3 vertices, you have your tau vertices and you have your B. So the bottom line here is this is a lot richer environment for us to actually investigate these techniques. And that's exactly the next proof of concept that we'll work on. What we also want to work on is what you've heard earlier this morning is these low-level information. So vertices, tracks, track qualities, PID. And in fact, and then we want to essentially do stage classifications where you try to classify subsets of that event and then build up on those subsets. So I think it's a common theme of what was presented earlier on this morning in terms of what we want to try to achieve. And we've already achieved that for that previous analysis, but now we want to look at more complicated events that really have eluded the Belle and the bar in the past. So in the interest of time, the next thing that we look at is the scalable deep learning. So what we've shown you is physics analyses, but what we really want to move towards is analyses that would allow us to do things that in the past we didn't think really feasible. And so this enters the MATEX framework. So MATEX is essentially an infrastructure that allows us to effectively not change any of the work that we've done in terms of implementing our keras TensorFlow. Our Python scripts and all that stay the same, but the backend changes in the fact that now it allows us to do MPI jobs that actually allow to save processing time. So if you want more information, if you look at that item number 3, this is a website to find more information on MATEX. But we'll just show you just a glimpse of some of the results that we've been working on in terms of performance. And then, so this is, and so what we have here is essentially HEP image-like. So we're working very close with this experiment to finalize publishing all this information, but at this point we can't give all the results. So the bottom line is we're able to present at the very least what we see in terms of the computing performance, and then subsequently we'll be able to show more information. But for now, for this particular conference, I think it's appropriate to talk about the speed-ups that one would expect. So the bottom line here is what we have in the x-axis is the number of nodes that we're actually using. And this is again keras and TensorFlow versus the nominal speedup that you would expect. We measured. You have at the very end 32 cores. Nodes on Cori gives us about a 26 speedup. So that's a substantial speedup. So again, it's not a linear scaling. It's not exactly linear. Nonetheless, if you're actually pressed for time and you want some results in turnovers, that's actually not a bad thing to have. The reason why Belle 2 in particular is interested in this is because we really care about what's called the ITOP and and doing deep learning on what's called the ring image. That'll be my next slide, and how this would perform in terms of the Belle 2 particle identification system. So currently we're also now investigating these kind of studies on Titan and also the Summit Dev architecture so that we have a better sense of how this will land. So in terms of the ITOP, this is one of the key subdetectors in Belle 2 that provides particle identification information. The bottom line is what we have here is a quartz bar, and you have a charged particle goes in, it gives off a Cherenkov radiation. And so what you see in this top figure is a pixel ID versus a photon arrival time. And in the blue, you have a pion. And in the red is a kaon. So you can see there's a difference for the same energy in this context. Of course, in the real experiment, we don't see this many actual photons. We only get roughly about 25, so it's a lot sparse. It's much more sparse. Nonetheless, the purpose here is that in the past, we are currently using an analytical solution, and it's based on the track momentum and also the impact parameters, so angle and position. And so what we really want to, because it's analytical, if conditions change, that doesn't get captured necessarily. You'd have to have perturbations of the analytical solution. Previously, minimization solutions were considered prohibitive because of the large phase space and edge effects of this particular detector. But we now believe that there's a possibility to do this kind of a study with this scalable deep learning solution and putting this on the supercomputers. So again, this allows us now to do gives us the ability, this MATEX framework gives us the ability to investigate possible solutions that otherwise we would not have tried. So in order to actually access the NERSC system, we've also implemented a full infrastructure that allows us to leverage our virtualization technique, which is what I brought up earlier on. The idea here is that you create a Docker that uses the Belle 2 compute infrastructure. On top of that, we put in the MATEX infrastructure. We have a Docker that's registered to NERSC. So then we also have in our system what's called a DRAC system that allows us to submit jobs to these supercomputers. And again, this is grid jobs. These are not tailored jobs. These are really generic grid jobs. You don't have to do anything special. So it's not a totally dedicated, tuned access point. This is something that anybody in Belle 2 can now, in principle, submit a job there by just doing a global URL, job submit. So this allows people that don't have access to bigger and larger computer infrastructures to actually submit a job to do some interesting analytics. So in summary, so TensorFlow is now fully is available within the Belle 2 software infrastructure framework. We've used the Keras TensorFlow to show clear improvements on a particular analysis, which is a beta K-star gamma. We're now investigating much more complicated signals, such as a beta K-star tau tau. We're now working on workflows that have big jobs on GPUs, and I think GPUs is a key point here, such as on Titan. We're also looking at applications for ITOP images and how we can actually improve and provide a robust PID for Belle 2. It should be honest, too, that one of the ideas that's been floating around is well, you could probably have every subdetector have a neural net or whatever technique you want, but the aggregate hierarchical identification system can actually use a neural net on top, so it's nested again. So that's the other thing that we're investigating. And the final point is that we now have a framework that allows us to now submit jobs via the grid that leverages HPC systems to do large-scale deep learning. Thank you.
Other questions? Yeah.
Yeah, I just wanted to ask a bit about how MathTech works. Did you use like like obviously with it like let's say an API?
It's an API implementation. So in fact, one of the things that had to be modified was we had to go to npitch2 to make it work within the Docker containers. Otherwise, the linkage wouldn't work properly. So that
doesn't use like the normal distribution.
that's correct.
Okay.
Right.
And then how do you think about the speed up that you put in? Is that the time process with a number of examples?
That's correct.
Rather than getting an answer.
Right.
I have a question. Could you go to slide 7? Comparison with the BDPs and neural nets. Yeah, that one.
Yeah.
Did you use this, when you say TMBNN, is that the MLP, the shallow neural network library for TMBA?
Yeah, it's just a basic out of the box. So it's not terribly.
Yeah, well, that's the thing. So
Yeah.
TMBA is about 2 years now.
Yeah.
There's a deep learning library which is much more powerful than the BDT, which is why I sort of would say if you make any comparison, you really should use the DNN.
Yeah, they also have the integrated Keras and.
No, not the integrated
You're
Keras.
talking about-
There's a
okay, right.
standalone deep learning library, MTMBA,
Okay.
which is basically the default. You really shouldn't really use. Shallow is more of a legacy thing. So just so you know, and anyone who makes that sort of comparison, we should compare it with that library.
Okay.
When we do that. Any other questions for that? Okay, no one's saying.
Okay.
Yeah.